Okay, so in the last session we had solved some numericals related to heat engine and refrigerator, like which are um, numericals and thermodynamics. Okay, so because it's a big chapter, we have not covered all. We will try to solve some more numericals and thermodynamics. Okay, so numerical problems on thermodynamics. Okay, so okay. So, so let us say we draw a PV diagram. Okay. Okay. So this is a PV diagram. Okay. So let's say this is one, this is two, and this is three. Okay. So this is pressure on the y-axis, volume in the x-axis. Okay. So it is going from 1 to 2 means it is expanding. Going from 2 to 3 means it's compressing, and going from 3 to 1 means it's a constant volume. So it's a iso, and the pressure is increasing, and volume is remaining constant. Okay. So this is a isoporic and this is a isobaric. Pressure remains constant, isobaric. Pressure volume remains constant is isoporic. Okay. So the question is the net heat absorbed by the gas in this process. So the question is, what is the net heat absorbed by the gas in this process? Yes. Okay, so it will be like this. So it's a gas. It has become a kind of a cyclic process. Why cyclic process? Because it starts from one and it ends with one. Okay. So if this is the case, they are asking that what is the net heat added. Net heat means in a process heat will get added and heat will get rejected. So what is coming in and what is going out. So difference between what is coming in and what is going out is called net. Okay. So here we can apply the first law of thermodynamics. Okay. So we know our del Q is equal to del U plus del W. Okay. So, but you know it is a cyclic process. So it has come back to the position one. That means there is no change in temperature. Okay. So this del U is equal to 0 because del U is nothing but a CV into delta T. That's the change in internal energy. So because there is no change in temperature, because this is 0, that's why del U is equal to 0. See, in any cyclic process, del U will always be equal to 0. Okay. So then your del Q becomes equal to delta W. Okay. So there is a trick in this question. They could have asked what is the net work done. So you know work done in a PV diagram is area under the PV diagram. Area enclosed by the PV diagram. Okay. So the work done is this much area, the area of the triangle, right? So, but they have asked net heat. So, but because it is a cyclic process, net heat is equal to net work. Okay. So that is the trick here. Instead of working work done you could have easily done okay P delta V is the PV area under PV diagram is the work done, but they have asked heat. That's why the understanding that a cyclic process there is no internal energy change, so heat is equal to work. Okay, so with this Yeah, let us say this is my P1, so this is my pressure P1 and this is my pressure P2. Okay. So if this is the case and I know this is my volume, so so okay. They have given it as this in the picture. They have given this as V1, this as V2. Directly they have given. Okay. So the area, so heat is equal to work is equal to area under the area 1, 2, 3, right?
Yeah.
So area of a triangle is nothing but half into base into the height, right? It's a right angle triangle.
Yeah.
So how much is the base here? It will be like, say, this is the value of V1 from the origin. This is the value of V2 from the origin. So this will be kind of V1 minus V2. Okay, so this is V1 minus V2. And this is P1. This is kind of...
No, from origin it will be.
So this is kind of P1 minus P2, right?
Yeah.
So P1 minus P2. Okay. So now we know the base, we know the height, so we can get the area of the triangle, which is nothing but V1 minus V2 into
P1 minus P2.
So this is the answer. Okay. So now you can, any numerical like this, if it comes, you should be able to solve. Okay. Anything related to a PV diagram is given. If they find what is the work done, you know area under the PV diagram is nothing but work done.
Okay.
So that is one. We will do. You take a picture of this. We will do. See how this Warden comes PV diagram, because you know P delta we had done is the infinitesimal work. Okay, dW is equal to P delta V. Okay.
Yeah.
So this you have this PV diagram and you have something like this. Then this is your pressure, this is your volume, this. And so so this area actually is the infinitesimal work. Okay.
Yeah.
So this is P and this is your dV, and then dW is equal to P into dV, right?
Yeah.
So then W is equal to integration of dW integration of P dV, right? So how it is work done? Because suppose if you see a piston cylinder arrangement, okay? So it's a piston cylinder arrangement. This gas is under, let us say, pressure P. So this piston, if you see from the top view, it is nothing but a, let us say, it's a circular piston. Okay.
Yeah.
So this piston will have some, let us say, it will have some area A. Okay.
Yeah.
So that means this pressure P is acting against a area A. Okay.
Yeah.
So you know force is nothing but your pressure into area. Okay.
Yes.
And let us say because of this pressure, this piston goes up by some distance. Okay. Let us say because it is pressurizing the piston, the gas. So it let us say it moves by some distance. Let us say it moves by dx. Right. So what happens? Your work done is nothing but your force into distance. Force into dx. Right. Some force is acting on the piston. That into dx. So your force is nothing but your P into area of piston into dx, right? So this A dx is nothing but your volume, infinitesimal volume. So it will become P dV. Okay, so this is dW, you can say. So that from that concept we get the work done.
Understood.
So this type of numerical, anything if it comes, you should be able to do, right?
Yeah.
Any doubt?
No.
so we'll try to solve one more numerical. Okay. So they will give a PV diagram and they will ask you to find out the corresponding TP diagram. So they have, so let us say, um, so question number 2. So let us say this is my PV diagram. Okay. So this is my P and this is my V. Okay. So this is my PV diagram, and the gas goes like this. Let us say more slope is adiabatic, or let us say it is a isothermal process. So let us say it is something like this. Okay. So it goes from 1 to 2. Okay. So here they are saying P is equal to constant by V. Okay. Okay. So that means PV is equal to constant. So we know, like, ideal gas PV by T is equal to constant. Okay. So if it becomes PV is equal to constant, that implies that it's a isothermal process.
Yeah.
Like from 1 to 2 there is no
Temperature
change
is
in
also
temperature.
constant.
So that means it's a isothermal process. Okay.
Yeah.
But when it goes from 1 to 2, you can when it goes from 1 to 2, that means it's a expansion.
Yeah.
Okay. So the question is draw the corresponding TP diagram. Okay. TP diagram. So you have now PV diagram, you have to draw the corresponding TP diagram. Right. So let me put my curve here, and let me say, this is, let me say this is my temperature,
Pressure.
this is my pressure. Okay. So here you can see it is expanding. So expanding means here pressure has come down. So because the pressure is on the x-axis here, to come down it has to move in the leftward direction.
Yeah.
Okay. And also because the temperature remains constant, it has to be a straight line.
Yeah.
In TP the curve it will be a straight line. So it will be like this. Okay. So the point 1 will be here and point 2 will be here. Okay. So it will go like this.
Understood.
Okay. So these kind of questions will come. So you have to be very careful here. There in your options, there will be something like this also. Okay. The same thing,
opposite arrow.
There will be something like this also. So this also they will have put as 1 and this also put as 2. But this is not correct, because here the pressure is increasing, but actually your pressure is decreasing. So you have to be very careful and you have to ignore that one. So when there are two choices, there is a scope of one getting confused. Okay. So this is one more numerical which is important. Okay. 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 So there is one more numerical. We will try to do. Let's say this is numerical number 3. Okay. So it is something like this. So it starts at point A, goes to point B, and then goes to point C, then come back to its original position.
X and Y axis. P.
X and Y axis are like say, it has pressure, here you have pressure, and here you have volume. Okay. Sorry, no, we add the here. They have given. Okay, so in okay, so they have given pressure on x-axis and volume on, instead of PV diagram it is BP diagram.
Okay.
Okay, whatever it is. Okay. Okay. So they are saying heat supplied to the gas in the cycle is 5 joule. Okay. So the question is heat supplied to the gas is 5 joule. Okay. So the question is your is 5 joule. Okay. So that is the net heat. Okay. So the heat supplied to the gas is, so work done by the gas in the process CA. Okay. So the question is what is the
What?
work done in the process CA. Okay. So you have AB, CB, BC, BA and CA. Okay. So so the heat. So del Q is equal to del W, right? Here, right?
Yeah.
So so del W is nothing but, like say, work done in AB, work done in BC, and work done in CA.
CA.
Okay, so BC, what will be the work done? The total area under this. Okay, so from A to B, what will be the work done? From B to C, this much will be the work done, right? The complete area under the curve. Okay, but from A to B, the work done is zero, because it's a there is no change in volume. Okay, so the work done in this cycle is WAB plus WBC plus
CA.
WCA. Okay, so work done is equal to WAB plus WBC plus WCA. Okay, so this is the net heat supplied to the system. So net heat supplied to the system is equal to net work done. Okay. So net heat supplied is given. That means net heat is equal to net work done. That's what the first law of thermodynamics says. So here from A to B, the work done is zero, because there is no change in volume. Okay.
Yeah.
Okay. So from B to C, what is the work done? That we can find out. Okay. From B to C, give the okay. So they have given some values actually, so it is not visible. Let me find out what is that value. So they are saying this pressure, actually, you see here pressure is equal to 10. Okay. So volume is 1 to 2. Okay. So the volume, I think there is a confusion here. Actually, this is P and this is V, right? They have not the question is little bit wrong. This is pressure, this is volume. Okay.
Oh.
So the pressure is 10. Okay. So the pressure, they are saying pressure is 10. Okay. So let us say pressure is some 10 unit. Okay. So the pressure is 10 unit. And the volume is, the pressure is in Newton per meter square. Okay.
Yeah.
Pressure is in Newton per meter square and
cube.
volume is in meter
Meter
cube,
cube.
right? So volume is 1 to 2. Okay. So it is 1 meter cube and this is 2 meter cube, right? So your work done during process BC is equal to pressure into delta V. So pressure into W volume B, volume at point B minus volume at point C, right?
Yeah.
So this pressure is 10 Newton per meter square into 2 minus 1 meter cube. Okay. So this become 10 into 1 Newton meter, which is nothing but your joule. Okay. So this is actually your 10 joule. Okay. So in WBC, so this is 10, right? So this is 10 and this is 10 joule, right?
Yeah.
Then the question is, and the LHS is 5 joule, right? Now the question is, what is the work done in the process CA? So this work done will be 5 minus 10
minus 5
joule equal to minus 5 joule. So this is the answer. Okay.
Yeah.
So now you can correlate like how by using first law of thermodynamics that del Q is equal to delta W, and you know heat is equal to the work done in 3 different processes. So this is important concept you should know. Like if you have a single process, so if you have a single process, something like this, then work done is equal to the complete area under the PV diagram.
Yeah.
That is one important thing you should remember. Okay. So if you have a complete process, this is the work done. So that's why from C to B, the complete work done is, this is the complete work done from C to B. C to B, this is the work done. Then if you see from A to C, from A to C, the whatever we have found out now, this will be the work done. Okay. So area under the curve A to C. So this will be the work done from A to C. And finally this area inside the triangle, so this area will be your net work done. Okay.
Yeah.
It is the net work done. Okay, so we have solved 3 numerical. Okay, so we try to solve some more numerical. So the question is, for which combination of working temperature the efficiency of Carnot engine is the least. Okay, so the question is, for which combination of working temperature the efficiency of Carnot engine is least. Okay, so they have given different options, like say combination of temperature like 40K, 20K. That is one option. Then option B is 60K, 40K, 60K, 40K. Option C is 100K, 80K, 100K, 80K. And then option D is 80K, 60K. Okay. So these are the combination of temperature of source and sink. Okay, so the higher temperature will always be the source, the lower temperature will always be the sink. So this will be your T1, this will be your T2. Okay, so the question is, for which combination of working temperature? So these are all working temperature. The efficiency of Carnot engine will be the least. Okay, so for which combination efficiency of engine will be the least. Okay. So this is the question. So you know efficiency of Carnot engine is nothing but 1 minus T2 by T1. This you have to remember. So it will be the least. Okay. When it will be the least? When T2 by T1 is the highest. Okay.
Yeah.
When T2 by T1 is maximum, efficiency will be minimum, right?
Yeah.
And so you have to find out actually when it is maximum. So for A it will be 20 by 40, which is 0.5. Okay. For B it will be 40 by 60, which is equal to 0.66 or 2 by 3, right? Then for C it will be 80 by 100, which is equal to 0.8. Okay. Then for D it will be 6 by 8. Okay. So 6 by 8 also like a 0.7, 8, 7 are 56, so 0.75, right?
Yeah.
So out of this, which is the maximum? The third one. The third one is the maximum. Okay. So that's why this combination of 80, 180 is the answer, right?
Yeah.
So okay, so 80, 100 is the right answer. Okay. So then we'll try to do some numerical on specific heat. Now we have done mostly on efficiency related stuff. Okay. So okay, so they first we will try to find out the relationship between CV and R. Okay. So okay, so you have taken picture of this?
No.
Okay, fine. Okay. So you know that your Cp minus Cv is equal to R, right? And Cp by Cv is equal to gamma. So there can be a question like find out the relationship between Cv and R. So how to find it out? Okay. So this Cp minus Cv is equal to R, and again this Cp you can replace. So Cp is equal to Cv into gamma, right? So this Cp if you replace by gamma into Cv minus Cv into R, right?
Okay.
So that means Cv into gamma minus 1 is equal to R. That means Cv is equal to R by gamma minus 1. So this type of questions also can come. Okay. Okay. Fine. So we'll try to solve one numerical on specific heat. Okay. And there is one question like when the cycle tire bursts. So this is a subjective question kind of. What kind of process it is? So when it bursts, some inside the cycle it is under pressure. In the tire it is under pressure. So it will be under some pressure P1 into P1. So if there is some leak, what will happen if it bursts? The outside atmospheric pressure is low, inside the pressure is high. So definitely it is an expansion process. But the question is whether it is a adiabatic process or it is a isothermal process. So the answer it is a adiabatic process because there is no time for to happen it in a constant temperature. Okay, if it happens, if there is equilibrium and there is lot of time permitted for it to happen, so it will be isothermal expansion. But actually it is a adiabatic expansion because the heat. The heat it's not isothermal. The heat there is no time for the release of heat. So in a adiabatic process, you know del Q is equal to 0. So from process 1 to 2, 1 to 2, so in Carnot engine we have done like this, right? So, so from 1, 2, 3, 4. Okay, so these 1 to 2 which are having higher, lesser slope, that is isothermal. T is equal to constant. But 2 to 3, del Q is equal to 0. That is adiabatic. Okay.
Yeah.
So this bursting of cycle tire is a adiabatic process because when the expansion, so this is the process. It is a adiabatic expansion. There is no time for the heat to be dissipated.
Yeah.
But pressure decreases definitely because it becomes atmospheric pressure. Inside your pressure is high, so it becomes atmospheric pressure. That's why pressure decreases. And because it is expansion, it is spreading all through. So it's expansion. So the that's the answer. Okay. Okay, so something related to specific it will do. Okay, so we'll write down the question. What is the amount of heat needed to raise the temperature of gas in a cylinder that contains helium gas at STP by 15 degrees centigrade? Okay. So the question is, what is the amount of heat needed? Amount of heat needed. What is the amount of heat needed to raise the temperature of gas in a cylinder? To raise the temperature of gas of the cylinder is of capacity 44.8 liter. 44.8 liter that contains helium gas. That contains helium gas. So this is a tricky question. That contains helium gas at STP. Okay, at STP. That is called standard temperature and pressure. Okay, STP by 15 degrees centigrade. By 15 degree centigrade. So this is the question. What is the amount of heat needed? Okay. So you know amount of heat needed del Q is equal to mCp delta T. Okay. So we'll show this in the pictorial format. Or it just for the timing it is mc delta T. Mass into specific heat into rise in temperature. So you can represent it is like this. So I have a cylinder, okay. The cylinder is of capacity, let us say this cylinder is of capacity, let us say this is 44.8 liter. This is 44.8 liter. The cylinder has gas. The cylinder has gas inside it. And what is the gas? That gas is helium. Okay. Helium, which is a He, which is a inert gas. Okay. Yeah. That is group 8. Okay. Sorry, 18th group. Okay. 18th group. It is a helium and 44.8 and standard temperature and pressure. Okay. It is at standard temperature and pressure. So pressure is atmospheric pressure, and what is the standard temperature?
Temperature,
Huh.
room temperature, 27 degree.
27. What is standard temperature? 27 degree. So that
Room
is 300
temperature.
Kelvin.
Yeah.
Okay. So at standard temperature and pressure, if the volume is 22.4 liter. The volume of 1 mole of gas. Okay. So at STP, the volume of 1 mole of gas is equal to 22.4 liter, right? So here there because it is at STP, so one point is this is at STP. Okay. So because it is 44.8 liter, that means it is 2 moles. Okay. That means An is equal to 2.
Yeah.
Right. So N is equal to 2 mole and this actually this uh, you want to amount of heat need to raise the temperature of a gas cylinder of capacity 42. So here what is happening, the temperature they are raising the temperature but volume they are keeping constant.
44.2.
44. So that's why here the heat this instead of here at C you will use CB here because you are keeping the
Volume.
temperature constant, volume constant, you are just heating it. So you are just heating it but you are keeping the volume constant. So this is NCV delta T. Okay. So your delta Q will become instead of mass you can write number of moles also.
N, yeah.
N CV into
Delta.
T. Okay. So your N is 2 and your CV for this helium is a monoatomic gas.
Yeah.
So it is to be removed. See, normally we are taking nitrogen. Normally in atmosphere it is nitrogen. So for nitrogen, CV is equal to 5 by 2R and CP is equal to 7 by 2R. 7 by 2R. So CP, that is, so normally we have discussed that CV is equal to F by 2R. So F is degrees of freedom. Okay. So for monoatomic gas, this degrees of freedom F mono is equal to 3 actually. Right?
Yeah.
But for diatomic, F diatomic, this degrees of freedom is 5. That's why it is 5 by 2 and 7 by 2. But for helium, which is a monoatomic gas, it is a inert gas.
Yeah.
It does not create any bond. It has 8 electrons already in the outer cell.
Yeah.
So it's a monoatomic gas. For this, CV is equal to 3 by 2 R, not 5 by 2 R, but 3 by 2 R. Okay. So now you know CV. And you want to raise the temperature by 15 degrees. So del T will be 15 only. Okay. So this CV, which is equal to 3 by 2 R and into 15. Okay. So you should do del T in Kelvin, but because it is del T, does not matter. You will just add 273 before and after, and you will get it. Okay. So. Okay. So the this R value you know is 8.31. Okay. So R is the universal gas constant, which is 8.31 joule Kelvin, joule per joule.
Mole inverse.
So you know PV is equal to nRT. So R is equal to PV by NT. So which is in standard it is 8.314 joule per mole Kelvin, right?
Yeah.
So that you know. So this is 2 into 3 by 2 into 8.31 into 15. So that will be your answer.
8.31 into 10 power something is
Okay, so whatever, maybe your 8.314 joule, whatever it is, you just understand the
there.
concept. So R value, how much it is, 8.31 into whatever,
Yeah. Into
you
10
find
power
out.
minus 34.
Minus 34. Okay, so I think you just have a reference. So here it is coming out to be 374 joules. Okay.
Okay.
So now you understand the importance of heat as the specific heat, okay? And what is CV now you can understand here. This volume is 22.4, you are keeping it constant, that's why, and you are raising the temperature. So work done, there is no work done because volume is not changing. Heat, whatever you are giving, it is just raising the temperature. Because you are keeping the volume constant, it is CV. And it is mCV into delta T, or it can be nCV into delta T also. So knowing the R in terms of mole and temperature, right, you can find out the heat required to raise the temperature of 2 moles of gas by 15 degrees. So here another thing is that at STP, the volume occupied by 1 mole of gas,
22.
irrespective of which gas it is, does not matter. Any gas at STP will occupy 22.4 liter of volume. Okay.
Yeah.
So we have solved the numericals on PV diagram, and we have solved numericals on specific heat, and something related to Carnot engine efficiency. Yesterday we have done heat engine and refrigerator.
COP.
So now with this, whatever problem comes in thermodynamics related to heat engine and refrigerator, specific heat, PV diagram, closed PV diagram, or only one line of a PV diagram corresponding to PV, what should be TP and all, that you should be able to do.
Yeah.
Okay, thank you.